Welcome to the Explainer! Today we're unlocking the secrets of one of the absolute most iconic microprocessors ever made, the 8085. If you've been grinding through computer architecture and wondering how does the physical hardware actually talk to the software, well, you're in the exact right place. We're going to completely bridge that gap today. Okay, let's dive into this.
Now, for those of you following along with your academic journey, specifically the Bangalore University BCA curriculum, this explainer is mapped directly to your Unit 4 syllabus. You survived the theoretical groundwork, which is awesome. And now it's time to conquer the actual, practical assembly language programming of the 8085 chip. We're literally turning concepts into code.
Here's our roadmap for this explainer. We'll be hitting 1. Realizing the basic computer. 2. The programmer's model. 3. Writing your first program. 4. The 8085 instruction families. 5. Mastering addressing modes. And finally, 6. Bringing it all together.
All right, jumping into Section 1, Realizing the Basic Computer.
So, think back to Unit 3 for a second. You learned all about theoretical basic computer organization, right? Well, it's time to see how that theory becomes reality. On one side, you've got those abstract concepts, the accumulator, the program counter, the instruction register, and on the other side, we have the 8085 microprocessor. The thing to remember here is that the 8085 isn't just some new random topic. It's a physical, commercially built piece of silicon. It perfectly implements that exact same fetch, decode, execute cycle you've already studied. The theory hasn't changed at all. It's just been baked into a real chip.
Inside that chip, we have some very specific architectural blocks. You've got your arithmetic logic unit, an accumulator for doing the actual math. There's a flag register to track the status of those calculations. You've got 6 general purpose registers, plus your stack pointer and program counter to keep track of memory. And then, of course, the instruction register, decoder, and timing control, all wired up together via internal buses. But here's the absolutely crucial point. This hardware, it sits completely idle. It's kind of like a high-end sports car without a driver, until you give it commands. To actually control this specific hardware, you need its specific language, and that is 8085 assembly language.
So how does this chip actually communicate with the outside world? Through its 40-pin layout. Now listen closely. My #1 rule here is purpose over pins. Please do not try to blindly memorize 40 individual pin numbers. No way. Instead, group them logically by what they actually do. We have pins for addresses and data, and that includes that really clever multiplexed AD0 to AD7 bus, which saves a ton of physical space. We have control signals like read and write, power and clock signals, hardware interrupts, and serial I/O. If you just focus on understanding these functional groups, the whole pin diagram just kind of makes total sense.
Moving right along to Section 2, the programmer's model.
Now that we get the physical anatomy of the microprocessor, let's transition to how we actually interact with it as coders. The programmer's model is honestly beautifully simple. You don't need to stress about the internal instruction decoder or the temporary registers when you're writing code. You only care about the subset of registers you can actively manipulate. That's your 8-bit accumulator, the flag register, the stack pointer, the program counter, and those 6 general-purpose registers, B, C, D, E, H, and L. And what's super cool is you can actually pair these up, B with C, D with E, and H with L. Doing that lets you hold and manipulate full 16-bit data addresses, which is a real game changer.
Now, what's really interesting about this slide is how we classify the commands we give these registers. We can group them by function, stuff like moving data or doing arithmetic, but also by their word length, meaning 1 byte, 2 byte, or 3 byte instructions. Let's say you have a 3 byte instruction, like loading a 16-bit address. That actually takes up 3 sequential spots in memory. So your program counter automatically auto-increments. It fetches byte 1, then byte 2, then byte 3, feeding them perfectly, one by one, into the instruction cycle. Honestly, it's just pure mechanical elegance.
Section 3, Writing your first program. Theory and models are great and all, but the real thrill is making this microprocessor actually do something. Bringing a program to life takes a concrete 4-step workflow. First up, you write your logic out using readable English-like mnemonics. Think words like add or move. Second, you convert those mnemonics into hexadecimal machine code. You just look up their specific opcodes. Third, you load that hex code sequentially into memory at a specific starting address. And finally, you execute the program, making sure to trace the flags and register changes step by step just to make sure it all works right. Let's trace a real example right now, adding 2 numbers stored in memory. First up, LXI-H, 2000H.
This points our HL register pair directly to memory address 2000. It's a 3-byte instruction, so it occupies addresses 2500, 2501, and 2502. Next, MOVA, M, copies the data from that memory location straight into our accumulator. Then, INXH simply increments our pointer to the next address, 2001. Finally, ADDM takes that new number sitting in 2001 and adds it directly to the accumulator. Boom. Just like that, you've controlled the flow of bytes from physical memory right into the ALU.
All right, Section 4, the 8085 instruction families.
To write more complex algorithms, we're going to need a bigger vocabulary. But instead of memorizing hundreds of random opcodes, which is a total nightmare, think of them in these functional families. Data transfer instructions like MOV, LDA, and STA, they simply copy data around without touching the flags at all. Branching includes your JMP, call, RET, and hardware restarts like RST. Arithmetic gives you add, ADC for carry operations, sub, and INR, and DCR for incrementing or decrementing. Finally, logical handles all your bitwise operations, things like ANA, ORA, XRA, CMP, and rotating bits with RLC and RRC. Oh, and HLT just halts the machine entirely. Once you understand what a whole group is designed to accomplish, learning the individual commands is an absolute breeze.
Okay, get ready for a major aha moment. This is a complete Unit 1 loopback. Remember learning about BCD, binary coded decimal, and how adding them together sometimes resulted in these invalid hex values? You had to manually correct them by adding a 6, right? Well, guess what? The 8085 has a dedicated instruction for exactly that. DAA, or Decimal Adjust Accumulator. It physically checks the flags and the accumulator for you, and if a nibble is greater than 9, it automatically applies that +06H correction rule. You are essentially using a single assembly command to automate the math you had to do by hand back in Unit 1. How cool is that?
Using these instruction families, you can start constructing real algorithms, like say, finding the largest number in a block of data. It's like a giant puzzle. You simply initialize your HL pointer and set a counter in register C. You read a byte, then you use the CMP, compare, instruction on the very next byte. And here's a neat trick. The compare instruction brilliantly does a subtraction without actually storing the result. It only updates the flags. If the carry flag flips, you know a borrow occurred, which means your current number isn't the largest. So you update it, loop back using a jump if not 0 instruction, and just keep going until your counter hits 0. You can even use this exact same looping logic for a block transfer, moving whole chunks of data from one memory location to another just by updating your pointers.
Section 5. Mastering addressing modes.
We've got the hardware, we've got the vocabulary. Our final technical topic is figuring out how instructions actually locate their data. And this brilliantly illustrates the elegance of the 8085 design, because it gives you 5 different ways to find an operand. First, immediate. The data is hard-coded literally right there in the instruction, like grabbing the 32H in MVIA 32H. Second, register. The data is just sitting inside a CPU register like B or C. Third, direct. The instruction spells out the exact 16-bit memory address where the data lives. Fourth, indirect. The instruction points to a register pair, usually HL, which in turn holds the address of the data, kind of like a treasure map. And finally, implied, where the instruction itself, like complement accumulator or CMA, implies exactly what register is being operated on without you even needing to state it.
Finally, Section 6, bringing it all together.
We've covered a massive amount of ground today, from physical silicon pins all the way to abstract addressing modes. I really want you to look at this question on the screen and reflect on your own learning journey for a second. How does the 8085 chip unite everything you've learned this semester? Because what we're looking at isn't just some isolated topic. The 8085 is the keystone that locks your entire computer architecture curriculum right into place.
Think about it. Unit 1's number systems and BCD arithmetic, they're fully realized in the actual hardware via the DAA instruction and the flag register. Unit 3's theoretical fetch decode execute cycle, that is exactly what the 8085 chip is physically doing thousands of times a second. And now, here in Unit 4, you've learned the assembly language that acts as the bridge between them. You now have the power to write software that physically controls those logic gates and registers. You can write, you can trace, and you can debug real functioning machine code.
You see, you're no longer just studying computer architecture from a textbook, you are speaking its native language. With your new grasp of the 8085's instruction sets, addressing modes, and the programmer's model, you literally hold the keys to the machine. So my final question to you is this: What real-world hardware problem will you solve next with your new assembly powers? Keep coding, keep exploring, and thanks for joining me on this explainer.